So thank you again, Dr. Luna, for the introduction, and thank you to everyone for having me here today. It's a real pleasure to present alongside this group of professionals. So just to reiterate, my name is Isaac Hollingsworth. I am a U.S. Army veteran, and during my time in the military, I served as a geospatial engineer with the 5th Geospatial Processing Cell out of Fort Shafter, Hawaii. Currently, I do work with Dr. Luna and the team here at Tennessee Tech University, conducting photogeologic mapping of the Artemis III candidate landing regions. I'm here today to talk to you about the need for specialized lunar surface maps. During our initial effort of producing photogeologic maps for the Artemis III candidate landing regions, we recognized that to put astronauts on the moon for the first time in over 50 years, products needed to be explicitly made for traverse planning. My experience as a geospatial engineer has helped our team to identify some specific needs for specialized maps of the lunar surface. Next slide, please. Okay, in this presentation, I want to highlight the parallels between the National Geospatial-Intelligence Agency and U.S. Army defined specialized maps and map products needed for safe and efficient Artemis lunar exploration. We adopt and modify the U.S. Army's standard operating procedures to define a novel series of specialized maps for the moon. We also illustrate how existing lunar geospatial data sets can be leveraged to create these standardized map products to aid in scientific understanding and safety. Following the approach of the U.S. Army and the NGA, we first identified standard operating procedures from the U.S. Army's Army Techniques publications 3-34.80 for Earth-based maps that focused on trafficability, communications, and defense. The following is not a comprehensive list of all the specialized maps that the U.S. Army produces, but these are the most relevant to the Artemis initiative. These products being traversability map products such as cross-country mobility maps, linear obstacle maps, combined obstacle overlays, and traverse time maps. We also have our line of sight map products such as viewshed analysis maps, and lastly, resource map products such as construction resource maps. We recognize that the naming convention for Earth-based specialized maps should be different from the naming convention of lunar specialized maps due to the context of their environment. So we took it upon ourselves to rename a few of these products to be more fitting. So for traversability map products, we have lunar surface mobility maps and terrain obstacle maps, in addition to lunar-based combined obstacle overlays and traverse time maps. Next is our line of sight map products, being viewshed analysis maps. And lastly, for resource map products, we created resource distribution maps. Next slide, please. Okay, so I would like to now take this time to cycle through some examples and give everyone a visual representation of the products that we've created during our time mapping the Geologic landing regions, and specifically Landing Zone Site 2, as previously mentioned by Dr. Lunar, or Dr. Luna. See, there it is. The name's too similar. During her presentation, starting with traversability maps. So just a heads up, as I move forward with this presentation, I will be speaking about the maps themselves to the right of the screen. And firstly, we have a lunar surface mobility map. This product mimics the workflow and analytical process of the U.S. Army's cross-country mobility maps. The only difference between these products is the context of where this analysis is performed. The main goal of a lunar surface mobility map is to identify areas of terrain that adhere to traverse parameters. In this case, slopes greater than 20 degrees are non-traversable. The map reflects these parameters by displaying areas where movement is unrestricted, unrestricted with caution, and restricted in a green to red gradient. Next slide, please. All right, next we have a terrain obstacle map, otherwise referred to as a linear obstacle product for analysis on Earth. These are products made to identify terrain barriers or hazards. Terrain obstacle maps of the moon illustrate barrier features of the lunar landscape, such as scarps, craters, troughs, and permanently shadowed regions shown in the map. The intent is to create a visual aid that decision makers can use to assess the risk of hazards in potential traverse sites. Next slide, please. All right, here we have a combined obstacle overlay. Now, the combined obstacle overlay map product provides a basis for identifying mobility corridors. Unlike the lunar surface mobility product, this map integrates terrain obstacles as well as traversability into one single overlay. This product depicts areas where astronauts can move unimpeded, as well as where movement is impeded or even impossible. So if I can direct your attention to the map on the screen, you can see that without terrain obstacle data, mission planners would be led to believe that the landing zone has a large area of unrestricted terrain. However, when the terrain obstacle data is applied, users are presented with a different story. While slope values are within the unrestricted range, a large portion of this area features permanently shadowed regions, as shown within the red checkered symbology. This product provides the most information that can be gathered from image-based data collection and maximizes the ability to mission plan. Next slide, please. All right, lastly, for traversability maps, we present a traverse time map. While the techniques used to produce a traverse time map are not new, the process of generating data accurate to the lunar surface proved to be a challenge. Traverse time analysis takes into consideration the effects that terrain has on pace using complex algorithms. And while there are many algorithms that can be applied to traverse time analysis, by and large, the most popular is Tobler's hiking function. The issue that was encountered when performing this analysis was that for astronaut traverse, a max speed of 2 kilometers per hour is defined, yet Tobler's hiking function is based on the preferred human walking speed standard of 5 kilometers per hour. As a result, the algorithm had to be adjusted by taking the percent decrease of pace from Earth-based standard and the defined max pace for lunar traverse. Once the mathematical details were resolved and data was produced that accurately aligned with mission standards, we designed a product that reflects this information. As you can see, the product features a series of rings surrounding the landing site. These rings represent radial distance from the lander in 200-meter intervals. The green to blue background represents time ring estimates based on the terrain in 10-minute intervals, which is why these rings are not perfectly circular around the landing site. This product gives mission planners a way to visualize the time dynamics of traverses in potential landing zones. This analysis excludes time spent at sample sites for collection, so this variable should be accounted for when estimating total route times. Next slide, please. All right, so here, now we're going to segue into our line of sight product. A viewshed analysis shows an area of observation that is possible from a 360-degree perspective based on elevation. Viewshed or line of sight analysis is used to identify the area over which an astronaut can traverse while still remaining in the line of sight of the lander. This is reflected in the map by the areas of color. A key factor of this analysis is that it can be produced rapidly, and this product provides important information pertaining to safety and will add an extra layer of assurance to mission planning. Next slide, please. All right, finally, for future work, as it was stated earlier by Dr. Bleacher, we recognize that to be able to produce certain specialized map products, data derived from EVA sample collection is required. It is no secret that our understanding of the moon is still limited by our lack of direct physical contact with the terrain. Lunar surface exploration, however, provides an opportunity to collect data that can be used for future map production. Higher resolution orbital data collection and data collected during EVAs can be used to produce specialized maps that are more detailed and accurate. The following is a sample product of how surface collected data can be used. The resource distribution map shown is a product that demonstrates the usefulness of specialized mapping for future mission planning. This product can help scientists and engineers plan for sustainable lunar construction and mining, and it also shows the locations and abundance of different surface materials, including geologic sample locations and water ice. Ultimately, this information helps identify areas of the moon that are suitable for a sustained lunar presence. Next slide, please. All right, to summarize, the use of specialized mapping standards inspired by military practices is crucial for the success of Artemis lunar landing missions. By developing and employing new lunar specialized mapping standards using the framework of the military, we can ensure accurate and reliable maps of the moon, which will be essential for safety and efficiency of lunar traverse. Just as mapping has been instrumental in guiding troops through unfamiliar terrain, these specialized maps will guide our astronauts as they explore the lunar surface. And by embracing the lessons learned by the military, we can pave the way for a successful and historic mission to the moon. Next slide, please. All right, I hope this speech has given you a better understanding of the importance of specialized maps for lunar exploration and how military specialized map products are the inspiration. Again, thank you so very much for your time, and thank you, everybody.